Imagine standing on a platform suspended 50 kilometers above the surface of Venus. Around you, golden clouds drift in the perpetual twilight. The temperature hovers near 75 degrees Fahrenheit, warm and pleasant against your skin. The pressure is nearly identical to Earth's at sea level. You could, in theory, breathe through a simple oxygen mask. No pressurized suit, no thermal shielding. Just you, standing in the atmosphere of another world, as casually as you might stand on a balcony overlooking the ocean. This is not science fiction. This is real atmospheric data from Venus, our closest planetary neighbor. A world we have been taught to dismiss as an absolute hellscape. Tonight, we're going to challenge something fundamental, an assumption so deeply woven into our collective imagination that it rarely gets questioned. We have been told repeatedly that Mars is humanity's destiny, our next great home, the logical stepping stone into the cosmos. Red deserts, ancient riverbeds, ice caps that whisper of water. Mars has captured our dreams because it feels familiar, almost romantic. But what if we've been looking in the wrong direction? What if Venus, the planet we've dismissed as impossible, might actually be more habitable than Mars in ways that sound absurd until you examine the science? This is not a simple story of one planet versus another. It is a journey into paradox. Venus might offer conditions friendlier to human life than Mars, yet simultaneously remain utterly, impossibly beyond our reach. How can both be true? How can a world with sulfuric acid clouds and surface temperatures hot enough to melt lead be more habitable than the cold red desert we've romanticized for centuries? The answer lies not on the surface, but in the atmosphere, in bizarre chemistry, in engineering concepts that sound like fantasy, and in scientific discoveries so recent they're still being debated in academic journals. Tonight, we will drift through Venus's crushing depths and Mars's frozen plains. We will explore cloud cities that could float like ships on an ocean of air, examine why radiation might be a greater threat than heat, and investigate the strange phosphine signatures that hint at the impossible, that Venus, beneath all its fury, might not be entirely lifeless. We will also confront the uncomfortable truths, the engineering nightmares, the chemical reactions that would dissolve our technology, and the philosophical questions about what it means to call a place habitable when we can never truly touch its ground. Before we begin this journey together, I have a small request. In the comments below, tell us where you are watching from and what time it is in your corner of the world. Are you drifting towards sleep as dawn breaks outside your window, or settling into the quiet hours before sunrise? This community spans continents and time zones, and there is something beautiful about knowing we are all looking up at the same sky, wondering about the same distant worlds, even as our clocks tell different stories. Now settle in. Let your preconceptions about Venus and Mars gently dissolve. What follows is not advocacy for one planet over another, but an invitation to see our solar system through fresh eyes, to question what we think we know, and to embrace the strange, unsettling truth that the universe rarely arranges itself according to our expectations. Venus has been waiting, shrouded in clouds and mystery. Perhaps it is time we looked closer. Let's begin. Earth does not exist in isolation. We occupy a middle ground between two planetary extremes, each representing a different path that a terrestrial world can take. To our left, Venus, a scorched realm of crushing pressures and temperatures hot enough to melt lead. To our right, Mars, a frozen desert where carbon dioxide snows onto the polar caps, and the atmosphere is thinner than the edge of Earth's stratosphere. These are our closest neighbors, and for much of human history, we misunderstood them both. There was a time, not so long ago, when Venus was considered Earth's twin sister. In the early 20th century, astronomers gazed at Venus through their telescopes and saw a world shrouded in thick, perpetual clouds. The planet's size was nearly identical to Earth's. Its mass was similar. Its orbit placed it squarely within the habitable zone, that precious region around the Sun, where liquid water could theoretically exist. The clouds suggested an active water cycle, perhaps oceans hidden beneath perpetual mists. Some scientists imagined tropical jungles teeming with life. Others pictured carboniferous swamps similar to Earth's ancient past, dense with vegetation and possibly inhabited by unknown creatures. Venus, after all, is named for the goddess of love and beauty. It shines brilliantly in our sky, brighter than any star, visible even in twilight. It seemed fitting that such a radiant world might harbour life. Popular science fiction of the era embraced this vision wholeheartedly. Stories set on Venus depicted explorers hacking through alien rainforests or encountering civilizations beneath the clouds. Venus was not just a candidate for life, it was expected to have life. Mars, meanwhile, received its own share of attention, particularly after astronomer Percival Lowell popularized the idea of Martian canals in the late 1800s. But Mars was colder, farther from the Sun, and its atmosphere appeared thinner. Venus seemed the more promising destination, the more Earth-like world waiting to be discovered. Then came the space age, and everything changed. In the 1960s, humanity began sending mechanical emissaries to explore our neighboring worlds. The Soviet Union launched the first successful missions to Venus, the Venera program. These spacecraft were designed to penetrate Venus's thick atmosphere and reveal what lay beneath those enigmatic clouds. What they discovered was not a tropical paradise, but a vision of planetary hell. Venera 4, arriving in 1967, transmitted data as it descended through the atmosphere before going silent. The readings were shocking. Temperatures exceeded 400 degrees Celsius. Atmospheric pressure crushed the probe long before it reached the surface. Subsequent missions confirmed and expanded these findings. Venera 7 in 1970 became the first spacecraft to successfully transmit data from Venus's surface. It survived for 23 minutes in an environment more hostile than the deepest ocean trenches on Earth. The surface temperature was revealed to be around 465 degrees Celsius, hot enough to glow faintly in the darkness. The atmospheric pressure was 92 times that of Earth's, equivalent to being nearly a kilometre beneath the ocean. The clouds were not water vapour, but sulfuric acid. Venus was not Earth's twin. It was Earth's nightmare. This revelation coincided with humanity's growing focus on Mars. The Mariner missions of the 1960s began mapping the Martian surface, revealing ancient riverbeds, vast canyons, and evidence of a world that once held liquid water. While Mars was cold and its atmosphere thin, it was not immediately lethal. A human in a spacesuit could theoretically stand on Mars's surface. The same could never be said of Venus. The psychological impact of this discovery was profound. Venus, once the bright hope of interplanetary exploration, faded into the background of public consciousness. Mars became the destination of dreams. The cultural shift was swift and total. By the 1970s and 1980s, Mars dominated both scientific inquiry and popular imagination. NASA's Viking landers searched for life in Martian soil. Science fiction films depicted Martian colonies and terraforming projects. The idea of humans walking on Mars became a rallying point for space exploration. Venus, meanwhile, was relegated to the category of interesting but inhospitable, a cautionary tale about greenhouse effects and planetary evolution gone wrong. For decades, this remained the consensus. Mars was where we would go. Mars was where we could build a future. Venus was too extreme, too hostile, too fundamentally alien to human existence. The scientific community followed public interest. Mars missions multiplied. Venus missions became rare. But science does not remain static. Neither does our understanding of what makes a world habitable. In recent years, something unexpected has happened. Venus has begun to recapture scientific attention, not despite its extreme conditions, but because of them. New missions are being planned. New questions are being asked. Could life exist in Venus's clouds, high above the hellish surface where temperatures and pressures are surprisingly Earth-like? Could floating habitats someday drift through Venus's upper atmosphere, where the environment is far less hostile than Mars's frozen deserts? The discovery of phosphine gas in Venus's atmosphere in 2020, though controversial and still debated, sparked renewed interest in our scorched neighbour. Whether or not the phosphine detection proves accurate, it reminded the scientific community of a fundamental truth. We have barely explored Venus. Fewer than a dozen spacecraft have successfully transmitted data from its surface. We know more about Mars than we do about the planet next door. The tale of Venus and Mars is not just a story about two planets. It is a story about human perception, about how our assumptions shape our priorities. We chose Mars because it seemed familiar, because we could imagine ourselves there. We rejected Venus because it seemed impossible. But impossibility, as history shows, is often a matter of perspective. As we prepare to examine these two worlds in detail, it is worth remembering that both Venus and Mars have surprised us before. Both have challenged our expectations, and both continue to hold secrets that may reshape our understanding of what it means for a world to be habitable. The question is not which planet is more like Earth, but which planet offers the most unexpected possibilities for humanity's future among the stars. Before we can understand why Venus might paradoxically be more hospitable than Mars, we must first encounter it as it truly is, a world of extremes, a planet that seems designed to destroy anything we might send there. Venus is not simply hot, it is an inferno wrapped in acid clouds, spinning backward through time. The surface of Venus exists at a temperature of 465 degrees Celsius, or 870 degrees Fahrenheit. This is hot enough to melt lead, to turn tin into liquid pools, to incinerate any spacecraft foolish enough to attempt a landing. Every probe humanity has ever sent to Venus's surface has survived only minutes, sometimes mere hours, before succumbing to the heat. Not because our engineering was flawed, but because the planet itself is relentless. The Soviet Venera landers, some of the most resilient machines ever built, transmitted their final images before being crushed and cooked into silence. But temperature is only the beginning. Venus's atmosphere bears down on the surface with a pressure 90 times greater than Earth's. To stand on Venus would be to experience the same crushing force felt half a mile beneath Earth's oceans. The weight of the air itself becomes a physical presence, a mass so dense it behaves more like a fluid than a gas. In this environment, even our strongest materials begin to deform. Glass warps, metal bends. The very concept of structure becomes negotiable. This hellish environment is the product of what scientists call a runaway greenhouse effect, the ultimate consequence of too much carbon dioxide and too little escape. Venus's atmosphere is 96% carbon dioxide. A blanket so thick and so effective at trapping heat that the planet radiates almost nothing back into space. The greenhouse effect that warms Earth to comfortable temperatures has, on Venus, become catastrophic. Heat enters, but cannot leave. It accumulates over millennia, baking the surface to temperatures that exceed even Mercury, despite Venus being farther from the Sun. And above this scorched landscape drift clouds that rain acid. Not water, but sulfuric acid, concentrated enough to dissolve metal. These yellow-white clouds form layers stretching dozens of miles into the sky, completely obscuring the surface from view. Lightning flickers within them, silent and perpetual. The clouds move fast, driven by winds that howl at over 200 miles per hour in the upper atmosphere, circling the entire planet in just 4 Earth days. Below, at the surface, the air barely moves at all, thick and sluggish like honey in winter. Venus presents another mystery, one that defies our expectations of how planets should behave. It rotates backward, while Earth, Mars, Jupiter, and nearly every other planet in our solar system spin counterclockwise when viewed from above the North Pole. Venus turns clockwise, a phenomenon called retrograde rotation. No one knows precisely why. Perhaps it was struck by a massive object early in its history, knocked into a cosmic tumble from which it never recovered. Perhaps gravitational interactions with the Sun gradually reversed its spin over billions of years. The mystery remains unsolved. More puzzling still, Venus rotates extraordinarily slowly. One Venusian day, the time it takes for the planet to complete a single rotation, lasts 243 Earth days. This is longer than a Venusian year, which takes only 225 Earth days. On Venus, a day is longer than a year. The Sun rises in the west and sets in the east, moving so slowly across the sky that it would be imperceptible to human eyes. Sunrise to sunset spans months. To witness a full rotation of Venus is to watch time itself move at a different pace. But perhaps the greatest mystery of Venus is not what it has, but what it is missing. Water. Earth is covered with oceans. Mars once had rivers and lakes. Even distant icy moons harbour vast underground seas. Venus, by all rights, should have had oceans too. It formed from the same primordial disk as Earth, condensing from the same materials, likely with similar quantities of volatile compounds including water. Yet today, Venus is drier than any desert on Earth. Its atmosphere contains only trace amounts of water vapor, far less than our driest deserts hold. Where did all the water go? The answer lies in Venus's proximity to the Sun and the tragedy of a planet that warmed too quickly. Early in its history, when Venus was young and the Sun was dimmer, the planet may have been temperate. Some models suggest Venus could have maintained liquid water on its surface for as long as 2 or even 3 billion years. Imagine it. A world with oceans beneath thick clouds, perhaps even primitive life stirring in warm tidal pools. Not so different from early Earth. But something went wrong. As the Sun gradually brightened over billions of years, Venus received more and more solar energy. Water began to evaporate. Water vapor, itself a potent greenhouse gas, trapped more heat. This caused more evaporation, which trapped more heat still. A feedback loop formed, unstoppable and irreversible. Eventually, the oceans boiled away completely. Water vapor rose high into the atmosphere, where ultraviolet light from the Sun broke it apart into hydrogen and oxygen. The lightweight hydrogen escaped into space, lost forever. The oxygen reacted with rocks on the surface, binding into minerals. The water was gone, transformed into gas and stone, leaving behind only a memory written in isotope ratios. With no water to absorb carbon dioxide, with no plate tectonics to cycle carbon into the crust, with no life to transform atmosphere into rock, the CO2 accumulated. Volcanoes continued to outgas, adding more and more carbon dioxide to the air with no mechanism for removal. The greenhouse effect intensified, temperatures soared, the transformation became permanent. Venus today is what Earth could have become. A cautionary tale written in planetary geology. The thin line between paradise and perdition measured in orbital distance, in feedback loops, in the delicate balance of water and carbon. To understand Venus is to understand fragility itself. It is to recognize that habitability is not guaranteed, not permanent, and can be lost entirely through processes that, once begun, cannot be stopped. And yet, as we shall see, this hellish world may still harbour possibilities that Mars, for all its familiarity, cannot offer. Venus is not merely a warning. It is, improbably, an invitation. But first, we must understand what we are being invited to overcome. We turn our attention now to Mars, the crimson world that has captured human imagination for millennia. Unlike Venus, hidden beneath its crushing clouds, Mars reveals itself openly. Its surface, rust-red and scarred by time, glows faintly in the night sky of Earth, visible to the naked eye as a steady, warming ember among the cold white stars. For centuries, Mars has been humanity's neighbour of choice, the planet we dreamed of visiting, the world we imagined might harbour life, or at least the memory of it. Mars is smaller than Earth, roughly half the diameter, with a gravity just 38% of what we experience at home. Standing on the Martian surface would feel like carrying a lighter version of yourself, each step slightly easier, each movement subtly transformed. The atmosphere, thin and insubstantial, exerts a pressure of only 0.6% of Earth's. To breathe here is impossible. To survive here requires constant protection. The average temperature hovers around -60 degrees Celsius, cold enough to freeze carbon dioxide from the air into frost that glitters across the polar regions each winter. And yet, despite these harsh conditions, Mars feels approachable. It has a solid surface we could stand upon, walk across, build upon. Its days last 24 hours and 37 minutes, remarkably close to our own circadian rhythms. The planet tilts on its axis, much like Earth, creating seasons that progress through spring, summer, autumn, and winter, though each season lasts nearly twice as long. From orbit, we can see its mountains, valleys, and vast plains stretching to horizons unmarred by clouds. Mars does not hide itself behind veils of sulfuric acid. It lies open to observation, inviting us to understand it. The polar ice caps gleam white against the red landscape, composed of water ice layered with frozen carbon dioxide. These caps grow and recede with the seasons, a reminder that Mars is not entirely static. Beneath the surface, radar observations have revealed extensive deposits of water ice, perhaps enough to fill lakes or even small seas if it could somehow be melted and released. This presence of water, frozen though it is, ignites hope. Water is the currency of life as we know it, the medium in which chemistry becomes biology. But Mars was not always this cold, desolate world. The surface tells a different story, one written in ancient stone and carved by forces long since vanished. Across the Martian landscape, we find networks of valleys that branch and merge like river systems on Earth. We see dried lake beds, their boundaries still visible after billions of years. We observe deltas where rivers once emptied into standing bodies of water, depositing sediments in patterns that speak of flowing currents and persistent moisture. Some scientists believe that Mars once possessed an ocean covering much of its northern hemisphere, a body of water that could have been kilometers deep, stretching across a third of the planet's surface. The evidence is compelling, though not without debate. Ancient shorelines appear etched into the landscape at consistent elevations. Minerals that form only in the presence of liquid water have been detected from orbit and confirmed by rovers on the ground. Clay minerals, sulfates, and other chemical signatures paint a picture of a world where water was not merely present, but abundant. This was a Mars with a thicker atmosphere, warmer temperatures, and perhaps even rain clouds drifting across red skies. What happened to that world? The answer lies in Mars's size and the death of its magnetic field. Earth's molten iron core generates a powerful magnetic shield that deflects the solar wind, the stream of charged particles constantly flowing from the sun. Mars, being smaller, cooled more quickly. Its core solidified, its magnetic field collapsed, and the solar wind began stripping away the atmosphere molecule by molecule, particle by particle, over hundreds of millions of years. Without atmospheric pressure to sustain it, liquid water could no longer exist on the surface. The rivers dried up, the lakes evaporated, the oceans, if they existed, either froze and sublimated away, or sank into the regolith, the dusty soil that covers much of the planet. Mars transformed from a world that might have cradled life into the frozen desert we observe today. Yet this loss makes Mars no less fascinating. In fact, it deepens the mystery. If Mars once had rivers and lakes, might it also have had life? Could microorganisms have flourished in those ancient waters, perhaps leaving fossils behind, waiting to be discovered? These questions drive our exploration. For decades, we have sent robotic emissaries to Mars. Orbiters circle the planet, mapping its surface with cameras and instruments that see in wavelengths our eyes cannot. Rovers traverse the landscape, analyzing rocks, drilling into outcrops, searching for the chemical signatures of past habitability, spirit and opportunity, curiosity and perseverance. Each mission has revealed Mars layer by layer, teaching us that this world is far more complex than a simple red sphere. We have learned that Mars experiences dust storms that can envelop the entire planet, turning day into twilight for months at a time. We have discovered that liquid water may still flow occasionally in the form of seasonal brines, salty enough to remain liquid despite the cold. We have found organic molecules, the carbon-based building blocks of life, though whether they are biological or geological in origin remains uncertain. Every answer generates new questions. Every discovery hints at deeper mysteries. Mars holds a unique place in human culture, especially in the past century. It has been the setting for countless stories of colonization, terraforming, and new civilizations. Authors and filmmakers have imagined domed cities and underground habitats, planetary engineering that could thaw the frozen water and thicken the atmosphere once more. Mars represents not just a scientific curiosity, but a vision of humanity's future among the stars. This romanticized vision is powerful. Mars feels within reach, not in terms of distance alone, but in terms of possibility. We can imagine standing on its surface in a way that seems more tangible than floating above Venus's clouds. We can envision footprints in the rust-colored dust, habitats constructed from local materials, gardens growing in pressurized greenhouses. Mars invites us to dream of becoming a multi-planetary species. But dreams, however beautiful, must be measured against reality. As we continue to learn about Mars, we must also confront what it truly means to live on a world with no breathable air, no liquid water, no protection from radiation, and temperatures that would kill an unprotected human within minutes. Mars may be our neighbor of choice, but it is still a profoundly alien world. When we imagine human footsteps on another world, our minds almost always leap to Mars. The rusty sky, the soft crunch of dust under fragile boots, the distant sun hanging like a pale coin over a frozen horizon. Mars has become our cultural shorthand for the next place. But quietly, almost stubbornly, Venus sits closer to us, wrapped in its luminous clouds, hiding a very different kind of promise. To see that promise, we have to step away from the lava plains and the crushing surface. We have to rise, up into the sky of Venus itself, into a region where, strangely, things begin to look familiar. Around 50 to 60 kilometers above Venus's surface, the chaos softens. The blistering heat gives way to temperatures closer to a warm day on Earth. The crushing pressure relents, settling into something very close to the air at sea level. Here, in this narrow band of atmosphere, we find a world that, on paper, begins to look more habitable than the Martian ground we dream about. And this is where Venus quietly outshines Mars. The first advantage comes from the very thing that makes Venus so terrifying: its atmosphere. While Mars wears only a thin veil of gas, barely 1% of Earth's pressure, Venus is smothered beneath a sky of dense carbon dioxide, stacked nearly 100 times thicker than our own. On the ground, that's lethal. But higher up, that ocean of air becomes a shield. Radiation from space, cosmic rays, solar storms, the constant drizzle of charged particles is one of the most unforgiving challenges of living off Earth. Mars, with its weak magnetic field and tenuous atmosphere, offers almost no protection. A human standing on the Martian surface is exposed to far more radiation than on Earth, day after day, year after year. Every sunrise on Mars is another small gamble with cellular damage and long-term health. Venus, by contrast, is wrapped in armor. Even without a strong magnetic field, its sheer atmospheric depth absorbs and scatters much of the high-energy radiation that reaches it. At those cloud levels where floating habitats are imagined, models suggest that radiation exposure could be comparable to, or even lower than, that on Earth's surface. A sky so dense it crushes landers into failure becomes, from above, a protective blanket, softening the harshness of interplanetary space. Then there is sunlight. Life as we know it, and technology as we currently build it, are both creatures of light. Venus orbits closer to the Sun, bathing in almost twice the solar energy that reaches Earth. Mars, sitting farther out, receives less than half. For solar panels, this difference is profound. A platform floating in the Venusian sky would be awash in power. The clouds reflect, scatter, and diffuse the light. But overall, the energy available to harvest remains immense. In an environment where resupply is costly and fuel is precious, having sunlight in abundance is not just convenient, it is the difference between scraping by and building something stable. On Mars, sunlight is weaker and often obscured. Dust storms can darken the sky for weeks, wrapping entire regions in a twilight that starves solar panels and chills habitats. Any settlement there must contend with long stretches of power scarcity, planning around the moods of a dusty, distant sun. On Venus, the sun is relentless, but predictably so, a steady engine in the sky. Beneath that sky, another quiet advantage waits: gravity. Our bodies are tuned, cell by cell, to Earth's pull. On Mars, gravity is only about 38% of what we are used to. Over weeks, months, years, we do not yet fully know what that will mean. We have hints from life on the International Space Station, bone thinning, muscle atrophy, shifts in circulation and vision. Mars is not weightless, but it is a world where everything is too light, and our biology may struggle to understand where down truly is. Venus, however, pulls almost as strongly as Earth. About 90% of our home gravity. If you stood, impossibly, on the surface of Venus, your weight would feel nearly the same. In its sky, inside a floating habitat, the gravitational field remains essentially that of a full-bodied world. For the long arcs of human life, decades, not missions, this similarity could matter more than almost any other factor. Bones might stay denser, hearts might pump more normally. Children born there might grow in proportions nature already knows. Beyond shelter and gravity, Venus carries a second gift inside its air: chemistry. Its atmosphere is not just a suffocating blanket of carbon dioxide. Threaded through it are elements that industry and life both hunger for: carbon, oxygen, nitrogen, sulfur. On Earth, these are the building blocks of fertilizers, plastics, fuels, fabrics, medicines, and metals. On Venus, they drift freely as gases and aerosols, waiting for any clever system that can sift, separate, and transform them. Nitrogen, especially, is precious. Mars's air holds only a thin whisper of it. Venus, by contrast, has a meaningful fraction mixed into its dense atmosphere. Nitrogen is essential for growing food, for creating breathable air mixtures, for many industrial processes. A floating factory in Venus's skies could, in principle, draw raw materials directly from the air around it, turning deadly clouds into pipelines of useful molecules. The pressure of that air, while dangerous at the surface, also becomes strangely helpful in motion. In space, most worlds are hard to slow down at. They lack thick atmospheres, so visiting spacecraft must rely on fuel-heavy burns to decelerate. Mars's thin air helps a little, but not enough to make arrival simple. Landing there is a balance of parachutes, rockets, and careful timing, because the atmosphere is just thick enough to complicate things, and just thin enough to be unreliable. Venus is different. For a spacecraft, its atmosphere is a vast braking system. As probes plunge toward it, the air itself embraces them, bleeding away speed through friction. Heat shields glow, parachutes bloom, and the atmosphere does most of the work. This same property that melts hardy metal into slag can, if harnessed carefully, become an ally in entering orbit, delivering cargo, or even operating aircraft that float, glide, or hover in the skies. And here lies one of the most counterintuitive ideas in planetary colonization, that while the surface of Venus is almost certainly unreachable with current technology for long-term human presence, its atmosphere may be more forgiving than the ground of Mars. Designs for cloud cities in Venus's sky are not pure fantasy. Engineers have imagined vast, lighter-than-air structures filled with breathable air that, on Venus, would be buoyant, like helium on Earth. In such a habitat, humans would live not on rock, but within an endless ocean of cloud. Outside the walls, a toxic, corrosive atmosphere. Inside, shirt-sleeve temperatures, radiation levels similar to home, and gravity that feels right. Some scientists look at this combination, radiation shielding, abundant solar power, Earth-like gravity, rich atmospheric chemistry, and quietly argue that, in certain ways, building a floating settlement on Venus might be easier than carving a safe existence into the frozen, airless ground of Mars. Not simple, Not soon. Not without solving problems we barely know how to describe. The acid of Venus's clouds would eat through many common materials. Its winds and lightning, its unpredictable dynamics, all would demand new technologies, new instincts for survival. But in the balance of planetary trade-offs, Venus offers something Mars does not. The possibility of living in a layer of the world that cooperates with some of our deepest biological needs, even as the rest of the planet remains utterly hostile. Mars invites us to land. Venus invites us to float. In that invitation, strange as it seems, some see our closest neighbour not as a hell to be avoided, but as a challenge to be reimagined, a world where habitability might exist not on the ground, but in the sky. To understand why Venus might be more habitable than Mars, we first have to let go of a very old assumption. We keep asking the same question. Can we live on the surface? Venus quietly suggests a different question. What if we never touch the ground at all? Far above the crushing heat and pressure, between roughly 50 and 60 kilometers above Venus's surface, the planet changes character. Here, the atmosphere thins, temperatures cool, pressures relax. Instead of molten inferno, we find something far stranger, a hidden layer where conditions begin to resemble home. In this band of sky, the temperature hovers around 20 to 30 degrees Celsius. The pressure is close to 1 bar, the same gentle weight of air that wraps around Earth at sea level. The air here is still mostly carbon dioxide, still hostile to our lungs, laced with droplets of sulfuric acid. And yet, in terms of temperature and pressure alone, this region of Venus is one of the most Earth-like environments anywhere beyond our world. Not on the surface, not underground, but suspended in the clouds. This is what scientists sometimes call Venus's habitable zone. Not around the star, but inside the sky itself. If we were to float at these heights, we would not be crushed. Our spacecraft would not need to be made of submarine hulls. Our habitats would not have to withstand the rage of a 470-degree oven. We would drift in a world where, with the right protection and materials, a window could be only centimeters thick, not meters. Where stepping outside in a suit would be more like walking in the upper air of Earth than on the slopes of a blast furnace. It is here that an idea takes shape. Not a base, not a dome, a city of clouds. NASA once gave this idea a name, Havoc. The high-altitude Venus operational concept. On paper, it looks like something from a science fiction painting. A sleek airship, 130 meters long, gleaming white against the orange haze of Venus's sky. Solar panels stretch across its back, catching the light of a sun that shines almost twice as strong as it does on Earth. Below the lifting body hangs a pressurized habitat, a capsule of Earth-normal air, gently gliding above the endless clouds. Havoc unfolds not as a single mission, but as a progression. First, uncrewed robotic balloons, testing the winds, the chemistry, the durability of materials in this alien air. Then a short crewed mission, perhaps 30 days, orbiting within the cloud layer, dipping lower and rising higher on currents of gas. Eventually, if everything works, longer stays. Floating laboratories. Perhaps, one day, something we might dare to call a settlement. The secret to Havoc is not magic, it is density. On Mercury or Mars, there is no easy way to float. On the Moon, there is no atmosphere at all. But Venus is different. Its air is thick, heavy, made mostly of carbon dioxide. On Earth, hot air rises because it is less dense than cold air. On Venus, something even more convenient happens. The very mixture we breathe, nitrogen and oxygen, acts as a lifting gas. If you fill a balloon with pure oxygen and nitrogen on Earth, it will not rise. It has about the same density as the air around it. But on Venus, that same mixture is lighter than the surrounding carbon dioxide. It is effectively a built-in buoyancy system. Our breathable air is not just something we need to survive. It becomes a natural replacement for helium or hydrogen. This means that any sealed structure that holds Earth-like air can float in Venus's atmosphere, gently lifted by the very stuff we rely on to stay alive. A habitat becomes both life support system and balloon at once. The larger the volume, the stronger the lift. The more people and equipment inside, the more air you add, and the system supports its own weight. From this simple fact, entire visions emerge. Imagine enormous aerostats, their envelopes hundreds of meters across, drifting through Venus's twilight. Some shaped like traditional airships, elongated and streamlined, designed to navigate powerful winds circling the planet in a 4-day super rotation. Others, more like static platforms. Circular floating islands of composite materials and advanced fabrics, anchored in the sky by ballast systems and fine adjustments in buoyancy. Below the main lifting body, multi-level habitats could hang like lanterns, connected by ladders and lifts. Observation decks ring the underside, sheltered behind acid-resistant windows, looking out over a cloudscape with no ground in sight. Inside, pressure and temperature are comfortable. Gravity is nearly identical to Earth's, and radiation levels are far lower than on Mars, thanks to Venus's thick atmosphere acting as a planetary shield. Smaller aerostats drift nearby, acting as weather stations, communication relays, and mobile laboratories. Some could dip lower into the cloud layers to sample chemistry and temperature, then rise again to more stable levels. Others could climb to higher altitudes, chasing the changing light as Venus's slow day cycles passed. Solar panels, stretched over the tops of these vehicles, would drink deeply from the intense sunlight. Venus, closer to the sun than Earth, receives almost double the solar energy. Even filtered through clouds, that is a wealth of power for a civilization that lives in the sky. Yet for all its elegance, this dream runs into harsh details. The first enemy is the same that gives Venus its beauty, the clouds themselves. Venus's upper atmosphere is filled with tiny droplets of sulfuric acid, a substance that quietly dissolves many of the materials we use on Earth. Aluminum, steel, even some glass compositions suffer damage. Polymers break down, fabrics weaken. Any floating structure would need a skin made from materials that are chemically resistant for years or decades. Teflon-like fluoropolymers, exotic coatings, layered composites that can be renewed or replaced. Our future cities in the clouds would be equal parts aerospace engineering and chemistry. Then there is the wind. At 50 to 60 kilometers, Venus's atmosphere flows around the planet at tremendous speeds, hundreds of kilometers per hour. This superrotation means that even as the solid planet takes 243 Earth days to turn once, the sky races ahead, circling the world in a matter of days. A cloud city would not hover over one location. It would ride these rivers of air, orbiting the planet again and again in a constant aerial voyage. Structures must be shaped to survive turbulence, to flex gently instead of breaking, to handle shear forces as layers of atmosphere slide past one another. Anchors to the surface are impossible. There are no cables to the ground, no towers that reach through 50 kilometers of toxic air. Everything that is stable, everything that is safe, must be achieved by design, buoyancy, and control. Inside, life support becomes a perpetual balancing act. Air must be recycled. Water, scarce and precious in Venus's atmosphere, must be gathered slowly from trace amounts in the sky or brought from elsewhere. Maintenance happens under the shadow of a simple rule. A breach in the hull does not mean exposure to vacuum, as on Mars or in orbit, but to a dense, hot, acidic, carbon dioxide-rich gas. Spacesuits would not be bulky against vacuum, but armors against corrosion and poison. And yet, through all of these challenges, one thing quietly remains true. The physics works. No laws of nature are broken to imagine these cities. No unknown forms of propulsion or exotic materials that defy chemistry are required. Air buoyancy, solar power, composite skins, closed-loop life support, all of these are extensions of technologies humanity is already developing. Our probes have floated in Venus's atmosphere before, surviving for hours. Balloons have drifted there, returning data until their systems failed. The path from hours to days, from days to months is steep, but it is not imaginary. What makes Venus feel impossible is not the sky. It is our expectations. We are still a surface species. Our earliest stories are about land claimed, mountains climbed, soil tilled. Mars, even as a frozen desert, offers us the comforting fantasy of ground beneath our boots. Venus asks us to abandon that comfort, to accept that an entire planet may never be walked on by human feet, yet still be lived upon. This is a philosophical shift as much as an engineering one. To inhabit Venus would be to accept a life without true horizons, only cloud tops and sky. A life where down is 50 kilometers of storm and fire, and up is a sun filtered through orange haze. A civilization that never builds cities of stone, only structures of air and light, traveling forever on the winds of a world it will never touch. In that sense, Venus invites a different kind of imagination. Not conquest, not terraforming, but coexistence with the limits of a hostile world. Its clouds offer a corridor where physics gently says, "You can be here if you respect the boundaries." The cloud cities of Venus are not here yet. They may never be. But in the equations of buoyancy, in the sunlight that floods its sky, in the pressure and temperature bands that mirror Earth's own, there is an undeniable whisper. If we ever choose to live beyond our planet, not all homes must be carved from rock. Some might be built from air and held aloft by the very breath we take. We imagine Mars as a blank canvas, waiting patiently for us to arrive and start drawing cities on its rusty plains. In artwork and concept videos, domes gleam beneath a salmon sky. Dusty astronauts stand heroically against the horizon. It feels achievable in a way that Venus never does. Tangible, practical, almost close. But as we drift, in thought, toward that red horizon, details begin to sharpen. Beneath the romance of Mars or bust lies a far stranger, harsher reality. Not a new Earth, but a world that resists us at every level, physically, chemically, psychologically, and perhaps ultimately geologically. Mars is not just cold and dry. It is hostile in quiet, invisible ways that do not make it into movie posters. We begin with something we cannot see, cannot smell, cannot hear, but which would shape every moment of life there. Radiation. Above Earth, a magnetic field stretches like a protective bubble, deflecting charged particles from the sun and deep space. Our thick atmosphere scatters and absorbs what gets through. On Earth's surface, we live in a soft shadow beneath multiple layers of invisible armor. Mars has almost none of this. Its global magnetic field died long ago. Its atmosphere is a whisper, less than 1% the pressure of Earth's at sea level. High-energy particles from the sun and distant supernova rain almost unimpeded onto the Martian surface. Each one is a tiny bullet of ionizing energy, not instantly fatal, but relentlessly cumulative. Spacecraft like Curiosity and the Mars Science Laboratory have given us estimates. Living on the Martian surface, even inside a thin-walled habitat, could expose colonists to radiation doses far above Earth's natural background, enough to significantly increase cancer risk over a lifetime, enough to slowly damage blood-forming cells, nervous tissue, and DNA. The problem is not a single solar storm, though those can be dangerous. It is the constant drizzle over years. A child born on Mars might never know a truly low-radiation environment. The sky itself would be, in a sense, slightly radioactive. To survive, we would need to live not in domes of glass, but in shelters buried beneath meters of soil or rock, or wrapped in tanks of water, or surrounded by manufactured shielding thick enough to turn our habitats into underground ships moored in the regolith. Which leads us to another quiet complication: gravity, or more accurately, the lack of it. On Mars, you weigh just 38% of what you do on Earth. At first, this feels like a gift. Steps become light, jumps effortless, but our bodies are written for 1G. Bones remodel themselves based on the loads they carry. Muscles strengthen or weaken according to demand. Fluids in our bodies circulate in patterns that developed under Earth's pull. In orbit, astronauts float in microgravity for months. They exercise intensely every day, yet still lose bone density and muscle mass. Their hearts adapt to a world without up or down. When they return, walking can feel unfamiliar. Their bodies must remember gravity. On Mars, there is gravity, but it is less than half of what we evolved for. We do not yet know what decades of life at 0.38 grams does to a human body. The concern is not just muscle strength, but irreversible changes. Bones that never fully mineralize, hearts that adapt to pumping less forcefully, vision changes linked to fluid shifts, and for children born there, developing organs and skeletons shaped from the beginning in a weaker gravitational field. Would a Martian-born adult ever be able to safely visit Earth? Or would our gravity feel like a crushing weight, stressing a body built for lighter worlds? The answers are not yet known. We carry these questions with us like unanswered letters, sealed but heavy. If we step outside our hypothetical Martian habitat, we meet the next problem up close in every direction: the soil under our boots. Martian soil is not really soil in the earthly sense. It has never known the touch of roots or the chemistry of life. It is ground rock, dust, and salts baked for billions of years by radiation. And among those salts is something particularly unfriendly: perchlorate. Perchlorates are chlorine-oxygen compounds found across Mars's surface in surprising abundance. On Earth, they are used in rocket fuel and industrial processes. In humans, they interfere with the thyroid, disrupting hormone production. In high doses, they are toxic. Any attempt to grow food using Martian regolith would have to contend with this chemistry. The soil would need to be thoroughly processed, washed, or otherwise treated to remove or neutralize perchlorates. That process is not simple. It requires water, energy, and careful engineering, just to turn dirt into something that won't quietly poison the life we try to cultivate. And the soil has another, more insidious form: dust. Imagine a powder so fine it behaves almost like smoke, but made of sharp, angular grains. Imagine it becoming electrostatically charged, clinging to suits, seals, solar panels, airlocks, working its way into every crack and filter. On Mars, dust storms can envelop entire regions, sometimes the whole planet, for weeks. The air never becomes opaque like a solid wall. but the sky slowly turns into a diffuse haze of suspended particles. Each grain is a tiny abrasive. Together, they are sandpaper on machinery, lungs, and eyes. On the moon, early Apollo astronauts brought back lunar dust in their suits. It smelled, they said, like burnt gunpowder. It irritated their lungs and sinuses. Martian dust may be similar, but with the added complication of perchlorates and long-term exposure. A leak in an airlock, a damaged filter, an improperly cleaned suit. Over time, these become not just inconveniences, but health hazards. In this environment, the dream of open Martian cities gives way to something more constrained. Habitats sealed, equipment constantly cleaned, air endlessly filtered. The romantic image of walking beneath a glass dome fading into a more practical reality of corridors, airlocks, and pressure doors. And then there is the question of where exactly people will spend most of their time. Because of radiation, the most logical place to live on Mars is underground, or at least under thick shielding. Natural caves and lava tubes have been proposed as ready-made shelters. Regolith piled over a structure could serve as a protective blanket. But this solution has a human cost. Imagine a life lived mostly away from the sky. Windows must be small or heavily shielded. Time outside in a suit is carefully rationed. The horizon, that intuitive sense of openness, becomes something you visit, not inhabit. Psychology begins to matter. On Earth, even in dense cities, you can step outside, feel air, see clouds, track the sun across the sky. On Mars, outside is vacuum-thin air, freezing cold, blasting radiation, and a dust-laden wind. Inside, the environment is safe, but artificial. The same walls, the same corridors, the same few familiar faces. Early crews, carefully selected and trained, might endure this with purpose and discipline. But what about a settlement of hundreds? Thousands. Children growing up with no forest to run in, no ocean roar, no true night air. The challenges here are subtle, but deep. Isolation, confinement, monotony, and the ever-present knowledge that a few centimeters of metal and plastic separate you from an environment that cannot forgive a mistake. Underlying all of this are the fundamental resources needed to stay alive. Water, oxygen, power. Mars has water ice, locked in the poles and buried in the ground at various latitudes. It has carbon dioxide in abundance in its thin atmosphere. In theory, we can split CO2, harvest oxygen, melt ice, and recycle everything meticulously. But theory does not pay the energy bill. Extracting water from frozen ground requires heat. Separating oxygen from CO2 needs power-hungry machines. Every kilogram of equipment used to do this must itself be brought from Earth or built from local materials using more machines. On a cold, dim world, sunlight is weaker than on Earth. Dust storms can linger over solar farms, choking off power just when heaters and life support are needed most. Nuclear reactors can help, but they introduce their own complexities and risks. A Martian settlement begins to resemble a network of interdependent systems, each requiring constant oversight. A failure in any one of them can cascade. Redundancy, backup plans, and stockpiles become as essential as air. When we zoom out further, beyond individual habitats and machines, we arrive at one of the boldest and most controversial ideas: terraforming Mars. Turning a red desert into a world with rivers, seas, and a breathable sky. For decades, visions of releasing greenhouse gases, melting polar ice, and thickening the atmosphere have captured imaginations. The concept is simple to describe. Warm Mars, let its CO2 and water vapor outgas, create a thicker atmosphere, and let biology do the rest. but the planet itself may not cooperate. Recent studies suggest that Mars simply may not have enough accessible CO2 locked in its polar caps and soil to build the thick atmosphere we would need. Its weak gravity makes it easier for gases to escape to space over time. Without a magnetic field, the solar wind strips the upper atmosphere continuously. Terraforming Mars is not like flicking on a climate switch. It is more like trying to fill a leaky balloon with a very small pump. Even with optimistic assumptions, the timescales for meaningful change tend to stretch, not into decades, but into thousands or tens of thousands of years. Far beyond any human political horizon, far beyond any single civilization's memory. In that light, the dream of walking on a blue-green Mars under a thick sky becomes almost mythic. Not impossible in an absolute sense, but sitting at the edge of practicality, in a realm where engineering converges with geology and deep time. And so, when we hold Mars in our mind beside Venus, a strange symmetry appears. Venus is too much, too hot, too dense, too crushing. Mars is too little, too thin, too exposed, too fragile. Venus burns, Mars erodes. One world strips you with fire, the other with emptiness. The case against Mars is not that it is bad or unworthy of exploration. It is that the story we often tell about it, as an almost ready backup Earth, is incomplete. To live there would mean trading one plane of impossibility for another. Not a frontier of easy domes and quick fixes, but a slow negotiation with a reluctant planet, fought meter by meter, kilowatt by kilowatt, generation by generation. And in that sense, the red planet is not so different from its veiled sister. Both invite us to dream. Both resist our presence in ways we are only beginning to understand. For a moment, Venus can almost fool us. 50 kilometers above its surface, the pressure feels like home. The temperature dips into ranges our machines can tolerate, and sunlight still spills generously across the tops of the clouds. In that narrow atmospheric shell, Venus begins to look less like a nightmare and more like a strange, inverted version of Earth. A world where the ground is air, and survival means learning to live in the sky. But as we drift deeper into the details, Venus reveals why, for now, it remains an almost perfect illusion. A world that tempts us with habitability and then quietly withdraws it. The first and perhaps most profound problem is simple, but not small. On Venus, there is no safe place to stand. Any realistic human presence must remain afloat, indefinitely. No stepping outside a habitat to plant a flag in the soil. No pressurized rovers trundling over dusty plains. The surface of Venus, at 90 times Earth's atmospheric pressure and temperatures hot enough to melt lead, is a domain reserved for metal and minerals, not flesh and fabric. Our longest-lived landers have survived there not for months, but for minutes and hours. Imagine a city in Venus's skies. It does not rest on pillars. It does not anchor to mountains. It hangs forever in balance with its own buoyancy. Every gram of mass must be offset by the lifting power of a dense, hot, alien atmosphere. Every habitat, every laboratory, every greenhouse is part of a continuous calculation that cannot be allowed to fail, even once. On Earth, gravity is unforgiving, but the ground is patient. If a system fails, a plane can glide, a balloon can descend, a ship can drift. On Venus, failure means falling, down, through 50 kilometers of thickening air, into pressure and heat that will crush and cook any known spacecraft in moments. There is no emergency landing. There is only descent. All engineering on Venus must be designed around this one truth. Nothing can ever truly be allowed to stop flying. Even the sky itself is hostile. The clouds of Venus are not made of water droplets, like Earth's familiar gentle layers. They are steeped in sulfuric acid, a substance that burns through metal, plastics, and human skin with quiet, relentless chemistry. In this world, the rain that never reaches the ground is not life-giving. It is corrosive. Most materials we rely on in space exploration, aluminum, many steels, common polymers, would weaken and blister in weeks or months. The elegant solar panels that unfurl so gracefully near Earth would be etched and darkened, their surfaces slowly destroyed. The transparent domes of our imagined cloud cities would cloud over, pitted by microscopic acid droplets, until even the sky itself faded from view. Surviving here means more than sealing our habitats. It means reinventing them. We would need coatings that shrug off acid as easily as wax repels water. Structures made from exotic alloys, ceramics, or fluoropolymers that resist slow dissolution. Maintenance would not be an occasional inconvenience, but a constant ritual. Surfaces cleaned, replaced, reinforced. Every seam inspected, every gasket renewed, because the atmosphere is always quietly trying to unmake what we build. If Mars challenges us with emptiness, the thinness of its air, the scarcity of its warmth, Venus challenges us with presence. Its atmosphere is not nothing. It is too much of something intensely unfriendly. And yet, to even get these materials to Venus, we would have to win a different battle. The struggle to land and one day, to leave again. Mars is thin and slippery, a world where parachutes strain for grip. Venus, by contrast, wraps itself in a deep, heavy blanket of gas. To descend through that blanket is to wrestle with friction on a gigantic scale. A lander arrives blazing with heat, crushed by deceleration, slowed not just by parachutes, but by the sheer resistance of air that grows thicker and hotter with every kilometre. For orbiters and atmospheric probes, this density is a gift. Parachutes bloom, drag multiplies, and soft arrivals are possible. But for any mission that dreams of touching down and then leaving again, Venus's atmosphere is a towering barrier. To return from Venus's surface requires a rocket that can climb out of a gravity well almost as deep as Earth's, while starting from within air as dense as an ocean floor. The ascent vehicle must withstand the surface hellscape long enough to stabilize, pressurize, ignite, and then punch upward through kilometers of crushing, searing gas. The rocket that would do this is not small. It is not light, and every kilogram of it must be brought down first, in one piece, and kept alive until launch. Our current technology allows heroic one-way descents, brave landers that go down knowing they will never rise again. A round trip from Venus's surface, with humans aboard, remains far beyond our engineering reach. Even an automated sample return is a formidable, unsolved puzzle. In the clouds, at more comfortable altitudes, things become easier, but not easy. Launching a return rocket from a floating city is conceivable. Weightless in concept, enormous in technical complexity. Tanks, oxidizers, fuel lines, all must coexist with corrosion, turbulence, and the constant demand to remain buoyant. Even if we solve these puzzles, Venus would still test our patience in another, subtler way, through silence. As Venus swings behind the Sun from Earth's perspective, a configuration known as superior conjunction, our line of sight to the planet passes close to the Sun's seething corona. Radio waves that usually carry commands, data, and lifelines of human conversation are scattered and distorted by solar plasma. During these weeks, deep communication with Venus becomes difficult, sometimes impossible. Mars suffers from this too, but Venus, closer to the Sun, spends a larger fraction of its cycles in these challenging alignments. For a city in the clouds, this would mean predictable seasons of isolation, pre-planned commands, autonomous decisions, and the knowledge that, for a while, Earth's reassuring voice will fade. We often imagine colonists gazing up at a star-filled sky, linked by a clean radio beam to mission control. On Venus, there would be times when the sky above the clouds is dark, the Sun a brilliant disk, and Earth hidden somewhere beyond it, unreachable. In those weeks, Venus would feel very far away. Even between these periods, the nature of our relationship with the planet itself would remain unusual. On Mars, we dream of in situ resource utilization, mining regolith for metals, baking soil for water, cracking ice into oxygen and fuel. The surface is a warehouse of rock and frozen volatiles, waiting to be turned into architecture and atmosphere. On Venus, we cannot casually reach the ground. Our entire economy must hang in the air. Everything we use, we must either bring with us or harvest from the atmosphere itself. Carbon dioxide, nitrogen, traces of sulfur compounds, water vapor measured in parts per million. These become our ore bodies, our mines, our fields. We would design floating refineries, chemical plants in the sky, distilling acid into industrial feedstocks, splitting carbon dioxide into carbon and oxygen, condensing precious droplets of water from a parched, superheated gas. There is a certain elegance in this, a city sustained by the very medium that threatens it. But it also means profound limitations. No digging for metals, no quarrying stone, no drilling for geothermal heat. Any heavy industry that needs minerals must draw them from tiny fractions of the atmosphere or rely on shipments from elsewhere in the solar system. Venus becomes not a self-sufficient world, but an outpost perched atop a chemical ocean, pulling its lifeblood from diffuse, slow processes. And then, beneath all of this engineering, is something quieter, the human mind. We are creatures of surfaces. We evolved to stand on ground that pushes back, to feel weight under our feet, to see horizons shaped by mountains, plains, and seas. On Venus, in the habitable layer of its sky, there is no ground. Only cloud above, cloud below, and the knowledge that somewhere far beneath lies a landscape we can never safely touch. What does it do to a person to live their entire life without ever standing on a planet? To know that if you step outside without a tether, there is no down you can survive reaching. For some, this might be liberating. A life in the sky, unbound by geology, cradled by a perpetual sea of cloud. For others, it might be unsettling, even haunting. Homesickness, not just for Earth, but for the simple act of feeling rock beneath your boots. Psychology is as real a constraint as pressure and temperature. A Venusian cloud city would need more than engineering. It would need rituals, spaces, and stories that help its inhabitants make peace with a world they can only ever orbit, never truly inhabit. Between the acid, the gravity well, the communication blackouts, and the absence of a solid foothold, we encounter the final barrier: time. The technologies that might make Venus livable, advanced corrosion-proof materials, ultra-reliable floating infrastructure, compact and powerful energy systems, fully autonomous operations during communication gaps, and ascent vehicles that can climb from air to orbit in a single, seamless motion, are not fantasies. Many are visible on the horizon of research and development, but they are not here yet. To close all of these gaps would require decades of steady progress. New probes to test materials in Venus's skies, robotic factories to practice atmospheric harvesting, innovative propulsion systems tailored for thick atmospheres, and a growing confidence that we can build machines that thrive where humans cannot. Venus is not impossible because physics forbids it. It is impossible for now because we are still young as a spacefaring species. In the end, this is what makes Venus so strangely compelling. It sits in a narrow band of possibility, more Earth-like in size, gravity and energy than Mars, and yet wrapped in layers of difficulty that keep it just out of reach. A world that whispers, "You could live here," and then adds, "But not yet." In the soft quiet of space, as we imagine drifting through those sulfuric clouds, we can hold both truths at once. Venus may be more habitable than Mars in some ways. And still, today, it remains a dream suspended in an ocean of acid and heat, a reminder that habitability and accessibility are not the same thing, and that some of the most inviting worlds in the cosmos are still waiting for the tools and the time we have yet to create. The story of Venus took an unexpected turn in the year 2020. For decades, it had been the villain of the inner solar system, a place we used more as a warning than a destination. But then, a quiet signal emerged from its clouds, not a radio transmission, not a beacon, but a faint chemical whisper. Phosphine. To most of us, phosphine is an unfamiliar word. It doesn't glow in the dark. It doesn't leave a trail in the sky. It is a simple molecule, one phosphorus atom bound to 3 hydrogen atoms. On Earth, however, phosphine is not simple at all. It is rare, fragile, and difficult to make. In our atmosphere, it is produced in 2 main ways. Deep in the hearts of giant gas planets like Jupiter and Saturn, under immense pressures and violent conditions, and by life. Here on Earth, phosphine is associated with anaerobic environments, places without oxygen. It is found in swamps, in the guts of animals, in decaying organic material. Our technology can manufacture it, but in nature, it tends to appear where microbes thrive in the dark, away from the surface, quietly metabolizing. So when a team of scientists announced that they had detected phosphine high in the clouds of Venus, the implication was as unsettling as it was extraordinary. If the result was correct, it meant that something on Venus was making phosphine in quantities that defied our current understanding of non-biological chemistry. Not just a trace, but a signal strong enough to stand out from the planet's dense, swirling atmosphere. Venus, the world we had written off as sterilized by heat and acid, suddenly looked more like a mystery than a lesson in failure. The detection came from radio telescopes, including the powerful James Clerk Maxwell telescope in Hawaii and the ALMA array in Chile. By looking at the way Venus's atmosphere absorbed specific wavelengths of light, the researchers believed they saw the signature of phosphine about 50 to 60 kilometers above the surface, right in the region we often describe as Earth-like in temperature and pressure, a temperate layer floating above a furnace. On Earth, the presence of phosphine at that altitude, at that concentration, would immediately raise questions about life. Our models suggested that known geological processes, volcanism, lightning, photochemistry, could not easily produce the amount reported. If it wasn't a known chemical process, and it wasn't an error, then something unusual was happening. But science rarely moves in straight lines. The announcement did not settle a debate. It started one. Almost as soon as the paper was published, other teams began to re-examine the data. Some questioned the calibration of the instruments, pointing out that faint signals in noisy spectra can be easily misinterpreted. Others revisited the models of Venus's atmosphere, wondering if there were exotic, but still purely chemical paths to phosphine that had been overlooked. Reanalyses suggested that the phosphine signal might be weaker than first claimed, or perhaps not present at all. Some studies reported that, when processed under different assumptions, the spectral feature attributed to phosphine could vanish or be explained by sulfur dioxide, a common component of Venus's atmosphere. The story shifted from, "We found phosphine," to "Did we really?" and then to a more cautious, "We might have, but we're not sure why." This is how science breathes, with excitement, with skepticism, and with revision. The phosphine controversy did not prove that there is life in the clouds of Venus. It did something quieter and perhaps more important. It reminded us that we do not fully understand this world. Whether phosphine is truly there in abundance, present only in small amounts, or not present at all, the questions it raised remain. If phosphine exists on Venus, what makes it? An unknown chemical pathway, exotic mineral reactions at the very edge of what we consider plausible, or something living, microscopic, fragile, and clinging to droplets of sulfuric acid high above a tortured surface. Even beyond phosphine, Venus's atmosphere holds other puzzles. Astronomers have observed strange dark patches in the ultraviolet, markings that drift and change over time, absorbing sunlight more strongly than the surrounding clouds. Their exact composition is not yet known. Some have proposed iron compounds, others sulfur-based molecules, and a few, cautiously, have suggested they could be concentrations of complex organic material or even microbial colonies, adapted to an environment that would be utterly lethal to us. None of these ideas are confirmed. All of them stretch our imagination. Yet they sit within a broader context that is very real. Life on Earth has already proven itself far more adaptable than we once believed. We have discovered microbes living in boiling hydrothermal vents at the bottom of the ocean, in acidic hot springs, inside nuclear reactors, even kilometers deep within the crust, slowly metabolizing rock and chemical gradients in eternal darkness. We call them extremophils, but to them, their environment is normal. It is we who are extreme. If life can survive in near-boiling acid or in highly alkaline lakes, if it can tolerate crushing pressures, freezing cold, and intense radiation, then the idea of microorganisms surviving in the relatively mild layer of Venus's atmosphere becomes less outlandish. Up there, temperatures hover around those of a warm day on Earth. Pressure is similar to sea level. The main difference is the composition of the air: carbon dioxide, nitrogen, and droplets of concentrated sulfuric acid. Unfriendly, but perhaps not impossible, especially if life had billions of years to adapt. The search for life on Venus, however, is fundamentally different from the search on Mars. On Mars, we look mostly down. We drill into rocks, sift through regolith, analyze sediments for signs of ancient rivers and lakes. We hunt for preserved organics, fossil biosignatures, relics of a warmer and wetter past. Mars, in many ways, is a graveyard we are gently excavating, hoping to find evidence that life once stirred there, even if it is gone now. On Venus, we look up. The surface is so hostile that anything exposed there is likely vaporized or crushed in moments. Rocks are baked, atmospheres thick, and time on the surface is short for any machine we send. Instead of fossils in stone, we search for chemistry in the clouds. Not the remains of life long dead, but hints that something might still be happening today in real time. This shift in focus transforms Venus from a tomb into a potential ecosystem. Thin, precarious, and alien, but an ecosystem nonetheless. It forces us to think of planets not as simple binaries, habitable or uninhabitable, but as layered worlds, where one region may be deadly and another marginally kind. In response to the phosphine debate and decades of neglect, interest in Venus has begun to surge again. Space agencies that once turned their eyes almost exclusively to Mars are planning to return to the planet we thought we understood, but clearly do not. NASA's Da Vinci Plus mission aims to plunge through Venus's atmosphere, sampling its chemistry directly as it falls, measuring noble gases, trace molecules, and the structure of the clouds with exquisite detail. It will not have to interpret distant spectral lines. It will taste the air itself, layer by layer, down to the surface. If phosphine or any other unusual compounds are truly present, Da Vinci Plus will help reveal where they are most abundant and how they behave. Veritas, another planned mission, will study Venus from orbit, mapping its surface with radar at far higher resolution than before. It will search for signs of past or present volcanism, tectonic activity, and resurfacing events. These processes could feed the atmosphere with gases, shaping its chemistry in ways we do not yet predict. To understand whether unusual molecules could be biological, we first need to understand what geology alone can do. Together with other proposed missions, including European and private concepts, these explorers mark the beginning of a new chapter. Venus, once considered a dead end for habitability, has become a laboratory for astrobiology. It is a place where we test not just our instruments but our assumptions about where life can thrive, how it might adapt, and how humble we must be when we look at another world and declare it impossible. The phosphine controversy may ultimately resolve in favor of mundane chemistry, or it may point to an entirely new category of atmospheric processes. It may even, one day, hint at biology. But its greatest contribution is already clear. It has transformed Venus in our minds from a static cautionary tale into an active question mark hanging bright in the morning and evening sky, asking us whether we truly know where life can and cannot be. The story of Venus and Mars is not just about two planets, it is about us and the way we imagine our place in the universe. For more than a century, when we dreamed of other worlds, our minds drifted almost automatically to Mars. It has valleys and mountains, polar ice caps that wax and wane with the seasons, a day only slightly longer than our own. In blurry telescope images and early spacecraft photos, Mars looked like a colder, drier version of Earth, a place where you could at least imagine standing on solid ground and seeing a horizon. That detail matters more than we tend to admit. Solid ground. Something to walk on. Something that feels familiar beneath our feet. Mars captured our imagination because it seemed like an extension of the landscapes we already know. You could sketch a Mars base and it looked like a rugged Antarctic station or a desert research outpost. Aluminum modules half buried in regolith. Solar panels dusted with red sand. Rovers tracing tire marks in a place that, at first glance, behaves like an ordinary world. Venus never received that same warmth. It hid beneath its clouds, refusing to reveal a comforting surface. When we finally peered below that global shroud, what we found did not feel like a home. It felt like a warning. Crushed probes, molten light, rocks baked in an atmosphere that could dissolve lead. The Venusian surface refused to become a backdrop for plausible sketches of human explorers. It did not lend itself to concept art posters or sci-fi cities on the ground. And so, almost without noticing, our shared dream of colonizing another planet narrowed. It became a story about Mars by default. But hidden inside that default is an assumption that real colonization means living on a solid surface, building cities on land, extending the familiar pattern of continents and coastlines into the sky. The concept of living in a planet's atmosphere drifting in the sky like ships at sea, feels less intuitive. Yet when we look at the numbers, at the pressures and temperatures and radiation levels, Venus's upper atmosphere begins to look less like a science fiction curiosity and more like a serious candidate. At altitudes around 50 to 60 kilometers, the environment outside a habitat could be close to room temperature. The pressure could be near 1 Earth atmosphere. The dense air above and below would act as a natural shield, softening the harshness of cosmic radiation. In this band of cloud and light, humans would not stand on a surface. They would float. Our hesitation here reveals a bias. Not a scientific one, but a psychological one. We are land animals. Evolution shaped us to trust things that are solid and still, even if they are cold and airless. A bare rock underfoot feels safer than a supportive fluid we do not understand, even when the rock is bathed in deadly radiation and the fluid could protect us. If we step back and compare Mars and Venus not as backdrops for our imagination, but as engineering problems, the story shifts again. On Mars, gravity is gentle, only about 38% of Earth's pull. That reduces the strain on structures and rockets, but it raises questions about us. We do not yet know how human bodies respond to years or generations of low gravity. Bones, muscles, circulation, even development in the womb may all behave differently. Radiation at the Martian surface, stripped of a thick atmosphere and global magnetic shield, is far higher than what we experience on Earth. Every step outside would require not just a suit, but persistent shielding in habitats, regolith piled overhead, or habitats buried beneath the ground. Resources on Mars are present, but thinly spread. Water ice is locked in polar caps and hidden reservoirs. Carbon dioxide fills the air, but the air itself is sparse. Fuel, air, and food would all require careful industrial cycles and closed loops. On Venus, the surface is a realm of extremes, but the skies above offer a different set of trade-offs. At the right altitude, temperatures and pressures sit in a narrow band that is strangely comfortable by planetary standards. The thick atmosphere below could supply carbon, nitrogen, sulfur, plenty of raw material for chemistry, agriculture, and manufacturing, at least in theory. The sunlight there is generous, filtered but strong. Radiation, muffled by the atmospheric blanket, would be less of a constant threat. Mars gives us ground with harsh air. Venus offers air with no accessible ground. Neither option is simple. Neither resembles a second Earth. In both cases, the word habitable can be misleading. It suggests that the world is waiting for us, slightly inconvenient but fundamentally welcoming. In truth, both Mars and the skies of Venus are hostile environments that only become livable through the careful construction of a technological bubble. Metal, polymers, recycling systems, power sources, life support. On Mars, inside a dome or buried habitat, you live in a sealed shell. On Venus, inside a floating station, you live in a sealed shell. Outside the walls, neither world is forgiving. From that perspective, the question, which is more habitable, becomes less about the planet and more about our engineering choices and our tolerance for certain types of risk. Mars asks us to endure cold, dryness, and radiation on a low-gravity desert. Venus asks us to trust buoyancy, chemistry, and storms in a sky without a stable surface. Yet Venus holds one more role in this story, one that extends far beyond colonization. It stands as a mirror for Earth's climate, tilted to an extreme. Beneath its reflective clouds lies an example of what happens when greenhouse effects run unchecked. Carbon dioxide presses down as a superheated blanket. Solar energy enters, but the heat cannot easily escape. Over time, the surface is transformed into an oven, the history of its water erased, its rocks annealed by relentless warmth. We do not know exactly how Venus became what it is today. Perhaps it was always destined for this path. Perhaps ancient oceans boiled away slowly, leaving behind a planet that remembers its lost seas only in chemistry, not in coastline. When we study Venus, we are not only unlocking the mysteries of another world, we are tracing the edges of what a climate system can do under different conditions, how sensitive atmospheres can be to composition, how feedback loops can amplify small changes into world-reshaping outcomes. In that sense, Venus is both a warning and a teacher. It shows us that a planet of roughly Earth's size can inhabit a completely different reality simply because its atmosphere took a different turn. As we contemplate sending machines or, someday, people to Venusian skies or Martian plains, another layer of questions emerges, ethical ones. Both planets may harbour environments that, in rare pockets or hidden niches, could support unfamiliar forms of chemistry, maybe even life. On Mars, subsurface brines and ancient riverbeds tempt us with possibilities of microbes hiding in the cold. On Venus, strange measurements in the clouds, like the debated Phosphine signature, hint at processes we do not yet understand. If life exists, or once existed, there is a delicate balance between study and disruption. Our spacecraft, no matter how carefully cleaned, carry traces of Earth, bacteria, spores, molecules from our biosphere. When we land, or when we drift through Venus's clouds, we risk mingling our biology with whatever foreign chemistry might be there. We also risk bringing back unknown materials to Earth, however unlikely their danger may be. Planetary protection guidelines are our attempt to move carefully, to explore without erasing what we are trying to observe. They reflect a quiet acknowledgement that alien worlds are not blank canvases. They are places with their own histories, their own potential stories of life and change. Colonization, if it ever occurs, shifts that balance dramatically. It transforms exploration into occupation, machines into infrastructure, a footprint into a settlement. At that point, we are not just visitors. We are participants in the planet's ongoing evolution. Some argue that life by its nature spreads, that if Earth can reach Mars or Venus, the universe is simply doing what it has always done, mixing, seeding, transforming. Others suggest a gentler path, to listen first, to understand as much as we can, for as long as we can, before we reshape another world to fit our needs. Between those views lies a wide, uncertain territory. In the soft glow of a distant sun, suspended above the clouds of Venus, or standing on the rust-coloured sands of Mars, the question is the same. What responsibility do we carry, as the first known species to move between planets with intention? Perhaps in the end, that is the most profound gift these harsh, unlikely homes offer us. They force us to rethink what it means to inhabit a world at all, to see that habitability is not just a checklist of temperature and pressure, but a relationship between life, technology, and a planet's deep, patient history. Mars, with its open deserts, and Venus, with its hidden sky roads, ask us not simply where we can go, but how we choose to arrive. For decades, Venus has been the bright world we mostly chose to ignore. A blazing lantern in our sky, passed over in favour of Mars's quiet, photogenic deserts. But that silence around Venus is ending. In mission planning rooms on Earth, in late-night proposal meetings and quiet simulations, something is shifting. The planet we once wrote off as a dead, toxic furnace is slowly being invited back into the story. The next chapter begins with a fall. Not ours, but that of a small probe diving into Venus's atmosphere, NASA's Da Vinci mission. Its name is an acronym, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging. But behind the technical language is a simple intention. We want to know who Venus used to be. Da Vinci will approach Venus the way we might approach an old, sealed archive. Carefully, patiently. It will measure the atmosphere layer by layer as it descends, reading the composition of gases like lines in a long-forgotten diary. Ratios of noble gases like argon and neon can reveal how much atmosphere Venus has lost. The chemistry of carbon dioxide and trace elements may hint at ancient oceans, or at least the possibility that they once existed. As the probe falls through the clouds, it will take images of the surface below, peering through gaps in the haze. The landscapes it glimpses, tessera highlands crumpled like ancient folded parchment, plains darkened by volcanic rock, may hold clues to whether Venus ever had continents, or something like plate tectonics, whether it was once more Earth-like than we dared imagine. Da Vinci's descent will last less than an hour. Its life will be measured in minutes near the surface. But in that brief window, it could help answer a question we've been circling for generations. Was Venus ever habitable in the way we understand habitability? Or did it follow a completely different path from the very beginning? While Da Vinci dives, another mission will orbit and listen. Veritas, also from NASA, is named for truth. It will not touch the surface. Instead, it will map it with radar, wrapping Venus in a high-resolution portrait, finer than anything we've ever had. The last time we saw Venus in detail from orbit was in the 1990s, when the Magellan spacecraft used radar to pierce the clouds. Its maps were revolutionary, but coarse, like seeing a mountain range at dusk instead of in daylight. Veritas will sharpen that vision. It will measure the shape of the planet with exquisite precision, detecting small rises and falls in elevation that might betray active volcanoes, shifting crust, or even hints of lingering geological heat. It will search for signs that lava has flowed in the recent past, that something under Venus's thick crust is still restless. If Venus is geologically alive, if its volcanoes are still breathing out gases into the atmosphere, that changes the way we understand its evolution. It might mean the hellscape we see today is not a static punishment, but an ongoing process, a planet still negotiating its own identity. Across the ocean, ESA's Envision mission will join this quiet symphony of observation. Envision will complement Veritas, focusing on how the surface and atmosphere interact. It will probe beneath the crust with radar sounding, searching for layered structures, buried basins, and perhaps the scars of ancient oceans now long boiled away. Its instruments will study how gases circulate between the rocks and the sky, asking a subtle but profound question: is Venus still changing now, in real time? Taken together, Da Vinci, Veritas, and Envision form something like a planetary biography project. One mission looks at the atmosphere's chemistry and history. Another draws an intimate map of the surface and its structure. A third looks at how everything connects. Piece by piece, they may show us not just the Venus that exists today, but the sequence of events that turned a potentially gentle world into a runaway greenhouse. As these government missions take shape, another presence begins to stir at the edges of the conversation: the private sector. For years, Venus has been overshadowed in commercial dreams by Mars, with its surface bases and red horizons. But ideas about Venus have started to seep into startup pitch decks, into speculative studies, into small, daring proposals. Concept papers outline tiny atmospheric probes, sent cheaply and often, to float in the temperate cloud layers where pressures are Earth-like and temperatures are merely hot, not lethal. Venture groups quietly explore whether balloon platforms, simple and scalable, could gather high-value atmospheric data at a fraction of the traditional cost. Some private groups even sketch early concepts for precursor stations in the upper atmosphere, uncrewed, autonomous platforms that could test materials, radiation-hardened electronics, and long-duration balloon systems. These are not grand cloud cities, just tools. But tools, once built, invite use. A single successful, long-lived platform above Venus's clouds could change how we think about operating in extreme environments anywhere. Beyond technical details, there is something else at work. The allure of being first. Mars is crowded with plans. Venus is almost empty. For a private venture, that vacuum can look less like neglect and more like opportunity. Far in the distance, beyond missions already funded and those still on the drawing board, sits a slower, more patient vision. It begins not with colonies, but with outposts. Not cities, but laboratories. Imagine a chain of atmospheric research stations drifting in Venus's upper clouds, each one the size of a small bus or a modest house. They do not need to support people at first. They can be robotic, autonomous, instruments wrapped in protective shells, sampling aerosols, tracing winds, listening to the sigh of the super-rotating atmosphere as it rushes around the planet in a 4-day sprint. Later, perhaps, we might add short-duration crew visits, astronauts arriving in orbital stations, then transferring to temporary habs in the clouds for weeks at a time. Their work would be less about settlement and more about understanding. The chemistry of exotic cloud particles, the physics of extreme greenhouse climates, the limits of materials in corrosive air. These are not the dramatic images of science fiction. Not yet. No sprawling floating cities, no glowing spires above the haze. Just quiet outposts, stations like mountain observatories on Earth, clinging to a harsh environment to listen, measure, and learn. Over decades, if technology and will persist, these scattered laboratories could grow into something more continuous. A network, a presence. Not a second Earth. Not a backup planet, but a place we know well enough to accept as part of our working cosmos, rather than a mysterious, avoided neighbour. As Venus returns to the spotlight, something else begins to change in our broader conversation about space. The old question, Mars or Venus, softens into something more interesting. For a long time, Mars was framed as the obvious choice, cooler, drier, seemingly more manageable. Venus was the cautionary tale, the world that went wrong. But as we think more carefully about both, we start to see how each tells us a different part of the same story. Mars teaches us about loss, how a world can cool, its atmosphere thin, its water retreat beneath rock and ice. Venus teaches us about excess, how a world can trap heat, thicken its skies, and bury its own ocean beneath layers of cloud and fire. Between them, they mark the boundaries of what a rocky planet can become. The more precisely we measure Venus's atmosphere, the better we understand runaway greenhouse effects, not just in theory, but in practice. The more we map its surface, the more we learn about tectonics, volcanism, and climate feedbacks pushed to their extremes. These lessons feed back into our models of Earth, into our search for habitable exoplanets, and into our attempts to recognize when a distant world is balanced on the knife edge between comfort and catastrophe. In this light, the Venus versus Mars debate is not really a competition at all. It is a way of sharpening our questions. Every time we ask whether Venus might be more habitable aloft than Mars is on the ground, we're forced to confront what we mean by habitability in the first place. Is it just surface pressure and temperature? Is it radiation, resources, long-term stability, psychological comfort? Each answer pushes our ambitions and our technology in new directions. As space agencies and private companies sketch missions to both worlds, we benefit in subtle ways. New entry systems designed to survive Venus's atmosphere also help with high-speed arrivals at other planets. Advanced balloons that can operate in Venus's clouds inform aerostat designs for Mars and even Earth. High-temperature electronics created to endure the Venusian surface may someday run quietly on Mercury, on Io, or in industrial furnaces at home. In listening to our two neighbours, one frozen, one aflame, we refine the tools we'll need for every other destination. The future of Venus exploration is not a single breakthrough moment, but a gradual brightening. A handful of missions collecting data, a slow drift of interest from Mars-only narratives to a more balanced view of our planetary neighbourhood. A recognition that to understand the thin line that makes Earth possible, we must look closely at the worlds where that line was crossed. As Da Vinci falls, as Veritas maps, as Envision listens, and as private ventures quietly test the edges of what's possible, Venus begins to step out of its myth and into our plans, not as a paradise, not as a replacement, but as a mirror held up to our assumptions about life, climate, and what it means for a planet to be just right. In that mirror, somewhere between Mars's silence and Venus's fury, we may learn not only where we can go, but where we truly belong. As our journey between these two worlds comes to an end, we find ourselves in an unexpected place. The planet we were taught to fear as a furnace, Venus, has quietly revealed her softer side. Not on the surface where rock melts and metals rain, but high above, in a band of air where temperatures and pressures pass through something strangely familiar. A layer with Earth-like gravity, air dense enough to shield against radiation and micrometeoroids. An atmosphere so supportive that floating habitats are not fantasy illustrations, but engineering studies on real desks. By comparison, Mars, the beloved frontier, shows us its harsher truths. A sky too thin to protect us, temperatures that bite through steel and bone, dust that seeps into every crevice, and a gravity that may be too weak to sustain human bodies across generations. Venus, in some ways, offers more of what we recognize as home. Mars, in others, offers more room to breathe technologically, if not literally, and yet, for now, both remain impossible. Venus asks us to master chemistry, corrosion, and pressure in ways we have never attempted at scale. Mars asks us to rewrite biology, medicine, and closed-loop life support to endure an alien desert. Each world stands behind a wall of challenges that our present-day tools can only scratch. They are habitable in theory, but unforgiving in practice. This comparison does something quiet but profound. It bends our gaze back toward Earth. Against the acid skies of Venus and the frozen plains of Mars, our world appears almost impossibly gentle. Air that can be breathed without machinery, liquid water in open rivers and seas, a magnetic field and thick atmosphere that shield us without our noticing. In studying other planets, we learn how rare it is to find one where life fits naturally. Dreaming about cloud cities on Venus or buried habitats on Mars is not a waste of imagination. It is how we test the limits of what might be possible. Many of the technologies we will need to thrive there will begin as ideas we are told are unrealistic, unnecessary, or too ambitious. impossible dreams are often just early drafts of future engineering. If you've enjoyed drifting through these worlds tonight, you can gently tap like and subscribe if you'd like more quiet journeys through science and space. In the comments, you're welcome to share where you're listening from, your city, your country, or simply Earth. It helps turn this distant exploration into a shared voyage. If you'd like to support the channel a little more directly, YouTube membership is available as an optional way to help these long, carefully crafted episodes continue. There is never any obligation. Your time and curiosity are already a gift. As you rest, remember, our neighbouring planets are beautiful, harsh mirrors, showing us all the ways a world can almost work. In their storms, deserts, and acid clouds, they remind us how extraordinary it is that, on one small planet, water flows, air supports us, and life took hold. For tonight, we do not need to conquer Venus or Mars. It is enough to drift among them in thought, and to fall asleep under the quiet, protective sky of the only true home we have ever known.